The nationally funded UpLift project is a major contributor to the European Union's ambitious goal for climate-neutral aviation until 2050. On the basis of a short-range airplane, the potential of hydrogen as a climate-neutral energy source is currently being investigated. Short-range travelling is a very energy cost-sensitive business because it's in competition with ground-based transportation. Due to the progressive expansion of the hydrogen sector, prices are expected to drop significantly until 2050, making hydrogen likely to be more competitive than, for instance, sustainable aviation fuel. Hydrogen may therefore be a key measure to reduce the negative climate impact of the commercial aviation sector, which is expected to triple until 2050. Storing hydrogen in a liquid state at extremely low temperatures is an essential enabler for future hydrogen-powered aircraft. This is why the UpLift research project is investigating this topic in detail. Since the large hydrogen tanks are likely to be installed in the aft fuselage, minimizing the structural weight is a high-level objective. The drastic weight reduction potential triggered the decision to investigate novel composite cryotanks within the UpLift project. The test approach is based on a pressure-resistant cooling unit and a clamped inner composite cryotank cap. A composite outer tank cap is added to build up a representative volume between the tank shells in order to evaluate suitable insulation strategies. Safety is paramount for a future composite cryotank, which means that gas tightness and structural integrity need to be demonstrated beyond doubt. The only way to accomplish this is by testing representative prototypes under realistic structural and thermal boundary conditions. Furthermore, the manufacturing of the prototypes needs to be very close to the later envisaged production in order to find and eliminate possible weak points. Within the UpLift project, a test facility has been realized that is capable of testing full-scale tank components under the most critical conditions. Drawing and sustaining an excellent vacuum is the key to tank insulation effectiveness, which in turn determines the amount of unwanted hydrogen boil-off. Microcracks, outgassings and gas diffusion have to be eliminated to meet this demand. When a sufficient level of insulation has been established, an innovative cooling system based on nitrogen evaporation is activated to set the required temperature conditions. -180 degrees Celsius is the upper temperature limit that might occur during operation, which means this is also the relevant temperature for hydrogen permeation and leakage tests. Another very unique feature of the test facility is the drastic reduction of test gas, because only the small gap between the cooling unit and the inner tank will be filled with either forming gas, helium, or hydrogen. This reduces the testing costs in the case of helium and the risk of fire or even explosion when hydrogen is used as test gas. The achievable tank performance will be analyzed and evaluated by checking the strain distribution in the relevant pressure range from 1 to 10 bars. The hydrogen gas tightness of the inner tank and the effectiveness of the outer tank structure will be assessed by checking the vacuum quality during pressure buildup and by continuously monitoring the vacuum status under operational conditions. Hydrogen-powered short-range aircrafts are expected to enter service by 2035, which means that basic design decisions have to be made within the next 3 to 4 years. This puts the UpLift project in a perfect position to use the results for upcoming design decisions. Looking at the year 2050, the experiences gained with hydrogen-powered short-range aircraft and dedicated ground operations at the airport may well be the enabler for even larger hydrogen aircraft and longer ranges.